Okay, I hope all of you did well for the first midterm, but it turns out that some people did not do that well. Please don't be frustrated, okay? There are second midterms and the final exams, okay? So my intention for this lecture is that I don't want to flunk any of you, okay? That's my intention, okay? As a matter of fact, if possible, I want half of my students in this class to have a grade of A minus or better, okay? That is my goal. So please work hard, okay? If you have any problem regarding my teaching material, teaching style, or whatsoever, come to see me or come to see the TA, who is a very competent young man, okay? And I'm sure he can be very, very helpful, all right? Now, if you didn't do well for the first exam, it is quite okay, all right? Because you are probably not familiar with the style or the pattern of the exams, okay? Now, right now, you already have I think, a very good idea of what our exams will be, okay? So hopefully you can do better. You can prepare yourself better for the coming exams. Remember, I want to give you good grades. The purpose of this course, the first thing is, of course, help you to gain more knowledge in the area of control, okay? And hopefully by doing that, you are better prepared for your future challenges. Okay, what is your future challenge? Why do we come to here to study? Why do I become a member of this department? There is, I think, one major reason. That is, we want to become engineers, right? That is why we become students of mechanical engineering department, okay? We want to be engineers, and we want to be probably mechanical engineers. And I said it many, many times in different cases. The golden age of mechanical engineering is coming, okay? Why is computer science so hot for the past few decades? Because they have internet, which is commercially very, very valuable. A lot of money put into internet. We use internet every day. So that is where the money is. That is the reason why computer science is hot, okay? Why is EE so popular? Because in this market, we have mobile phones, we have computers. Everybody uses computers. Everybody uses mobile phones. And actually, everybody replace their mobile phones every 2 or 3 years. It depends on personal choice. But that is also where the money is. That is why EE is very hot. Now, for mechanical engineering, we didn't have such products such as internet, mobile phones, okay, smartphones, or computers. But we are one of the hottest products is coming, which is robots, human-like robots, okay? Robotics used to be an old technology. Why? Because to build a good robot, the first and the most important fundamental challenge is not build the body, is to build the brain. Okay, because as a human being, brain is the most important part for us, right? Brain controls pretty much everything, okay? Mentally and physically, and sometimes psychological, all right? And with AI, nowadays robots can behave like a human, but we still have to build them. And people are building them. Who are building them? Elon Musk and NVIDIA. So Tesla and NVIDIA, they all said it publicly. Humanoid robots will be their future, okay? They will have major investment in that area. And same thing happened in mainland China. They will build robots like they build electric cars, electric vehicles, okay? And robot is a mechanical engineering process. It involves kinematics, it involves dynamics. It requires knowledge of mechanism. It requires knowledge of mechanical engineering design and manufacturing. With all due respect, people from computer science and EE do not know shit about kinematics and dynamics, okay? Because they never take any course in that area, okay? They have no knowledge about gear trains, bearings, linkage, all right? They don't know how they work, okay? But as a mechanical engineering, we have been trained to be familiar with robots, okay? So the golden age of mechanical engineering coming. And when it comes to robotics, control, of course, play a very, very central role in building a good robot, okay? All right. Hopefully, I have provided some positive messages to you to motivate you to spend more time on learning control and spending more time on making yourself a better student of mechanical engineering, because it really has a good future. Let me put it this way. I really envy you, because when I was young, mechanical engineering is not hot, wasn't hot, okay? As you can see, for the past 2 decades, it is computer science and EE dominates the industry, okay? Now, and mechanical engineering probably only play the secondary role in those groundbreaking development process. But I think things are changing, okay? Things are changing, okay? I'm too old to see that changes will become reality, but you will definitely see that, okay? All right, let's go back to our revised spring mass damper system, whose transfer function looks like this. Again, this is the input, this is the output, this is the transfer function. Again, eta represents the damping ratio, and omega n is the natural frequency, okay? From this transfer function, you only see 2 parameters, eta, omega n, nothing else, okay? Damping ratio, natural frequency, nothing else, okay? So damping ratio and natural frequency, as we said it again and again and again, are the 2 key parameters for spring mass damper system or for linear time invariant second order system. Now, what we want to do here is we want to study the state response. So Rx here, since we have a state input, the Laplace transform of a step function is 1/x. So this is the state response in the x domain, all right? So we want to see what happened in the time domain because we want to see it, visualize the step patterns by our own eyes to see how the output of resistance changes with time. That is something we can comprehend easily, all right? So the first thing we do is that we assume eta is larger than 1, which correspond to the Overton case. And by taking the inverse Laplace transform, this is what we will get for the unit step response. Okay, for this part, you see that we have a constant output here. And when time goes to infinity, as long as S1 and X2, which are given here, and since we have the negative real part, these two will go to 0 when t goes to infinity. All right? So the steady state output in this case is of course 1. Now, how do we characterize the speed of response of this system? Since we have 2 modes, okay? Now, a system is only as fast as the slowest pole, okay? You have 2 distinct real poles. One is located here. The other is located here. Let's say S1 is -1. And let's say S2 is -9. So what you have, this is e to minus t, and this is e to minus 90. So this term will vanish, will decrease to 0 much faster than this, all right? So when it comes to speed of response, this mode is faster than this. Put it in another way, this pole is slower than this pole, okay? A system is only as fast as it slows the poles, okay? Because a system, how do you characterize the speed of response of a system? It determines how fast this term vanished completely, okay? So if one of them disappears and the other term remains, the term collectively is still here, okay? Still not completely gone. So this is the reason why we say a system is only as fast as its slowest pole, just as a chain is only as strong as its weakest link. It's an analogy, okay? Now let's switch to the second case, okay, which is underdamped case. And in this case, the value of eta is between 0 and 1. And here, in this case, the poles is a pair of complex conjugate numbers. And remember, omega d represents the damped natural frequency. And again, by taking the inverse Laplace transforms and by using partial fractal expansions, this is what we'll get. And by using these 2 inverse Laplace transform formulas, this is the unit step response for an underdamped system, all right? And again, it consists of 2 parts. The first part, again, is 1. The second part is the transient terms. The reason why it is transient is because of this. As long as eta omega n is positive, when t goes to infinity, this term will go to 0. So this term eventually will go away. So this represents the steady state output of the system, and this represents the transient proportion of the unit step response. All right. Now here we have a family of curves. Okay, because this family of curves all correspond to different damping ratios. Okay. For example, for the overdamped case, what you will see, the unit step, we can see that the unit step response approaches one gradually, one step at a time, without any acceleration. Okay, and then let's say you reduce the damping ratio from 2 to 1. Same pattern will emerge again, which means it will approach 1 without acceleration. But here, because with less damping, the speed of response is faster. But once the value of eta becomes smaller than 1, this is what happened. You will see accelerations. You will see overshoot. This part is overshoot. Sometimes overshoot is permissible. Sometimes overshoot is highly undesirable. It depends. But as you can see, it is easy to see how eta alter the speed response of the system, right? Because when eta becomes smaller and smaller and smaller, from this family of curves, you can see the unit step response of the system become faster, faster, and faster, right? But there is a price to pay for this increase or speed of response, which is overshoot. The higher the speed of response, the larger the overshoot. Okay, so this is essentially a trade-off. Okay, you cannot have both. Okay, you cannot have both. Now, we saw this picture before, okay, which illustrates the locations of a pair of complex conjugate poles, okay, and you can represent it by this Cartesian coordinate format, or you can represent it using polar coordinate format. Now, let's talk about the relationship between the speed of response and the two key parameters of the second order system. This figure demonstrates how step response of the second order LTI system depends on the damping ratio, right? Because these curves are curves of different damping ratio. Okay, let's move one step back. You can say, wait a minute. You just told me there are two key parameters for the second order system, which one is damping ratio, the other is natural frequency. This family of curves correspond to systems with different damping ratios. Well, is the natural frequency. What is the role of natural frequency? Okay, the role of natural frequency appear on the horizontal axis. Please pay special attention. Now, these curves, they do not vary directly with time. They vary with a normalized time, which is the product of time and the natural frequency of the system. Okay? All right. So this is a normalized time. Okay. By introducing these normalized times, we can compare systems of different damping ratios on the same universal basis. Okay. We will go back on this normalized. We would discuss this normalized frequency later, okay? That I can assure. Now, let's relate natural frequency and damping ratio to the unit step response of the second order system, all right? Omega n set the overspeed scales, okay? This is the reason that because the time variable here is omega nt. Now, please just accept this statement for the time being, okay? I will go deeper about this statement in the later part of this course. Eta show the transient behavior, including, right? Different eta, different transient behavior, including what? Overshoot, the amount of overshoot, the amount, the pattern of the oscillation, and how long it takes for the system to settle, okay? And lower eta value leads to oscillation, right? So the smaller the eta, the stronger the oscillation, while higher eta values result in slow, non-oscillatory returns to equilibrium. It highlights the trade-off between speed of response and overshoot as damping increases. Okay, when damping increases, the speed of response decreases and the overshoot also decreases. Okay, we want smaller overshoot, but slower speed of response is not something we preferred, because when we do things, we want to get it done as quick as possible, right? When you order something online, what do you expect? Do you expect they send you the product 1 week from now? Of course not. You expect they deliver in 24 hours, in 12 hours, even better in 3 hours, or even better in 1 hour, okay? And that could happen in the future. That could happen in the future. So this is the reason why I tell my students again and again, there is so much to anticipate, so much to look forward to in your later part of your life, okay? There's so many good things, so many great technology are coming, are emerging, okay? And your life will become much more productive, much more convenient, okay? Much more even breathtaking, all right, okay? So there is so much to improve as you age, okay? Now, together, omega n and eta completely determine the system time domain step response, all right? Now, here, let's look into the nature, the detail of the unit step response of the underdamped second order system. Now, we have this result, okay? This is the unit step response for the underdamped case, all right? Now, let me introduce a new time variable, which is dimensionless, and we denote it as lambda, and we define it as the product of natural frequency and time. So tau is simply omega n times t. Now, once I introduce this term, I can rewrite this representation as this new equations, okay? They are essentially the same. The only thing I do to go from here to here is whenever I see omega nt, I replace it by tau. Okay, so I have one omega nt here. I have another omega nt here. Okay, so in here, in this expression, whenever you see t, there is always an omega n ahead of it. Okay, so once I done that, t disappear entirely from this representation. And C, which is the output of the second order system, now become a function of tau. And then we can use different value of tau to generate this family of curves with an independent variable of tau. All right? That is the very reason why we call tau a normalized time. All right? Okay? And remember that we said it once that omega n sets the time scale of the system. What do I mean by that? Okay? Omega nt, which is defined as tau, is what we said it is a normalized time variable. Why do we want to do that? Why do we want to introduce tau? By normalizing time, the response curves of different systems was different or varying natural frequency or damping ratios can be compared on the universal basis. Okay, they be compared on the same basis. So fair comparison can be conducted. This is useful because systems with different natural frequencies will respond at different speeds. But normalizing allows us to focus on the shape of the response and an effect of the damping ratio eta rather than the absolute time. Okay, these statements are absolutely correct, but somewhat extra. Let's look at two simple examples. Remember that tau is omega n t. So t is essentially tau over omega n, right? So from this representation, we know that let's assume tau stay the same, a constant. All right? But if omega increases, tau decreases, right? They have an inverse relationship, as you can see from this equality. In contrast, when omega n decreases, t increases. What do I mean by that? When omega n increases, which means I have larger time frequency, and t decreases, which means to reach to the same destination. Now, the time required to do that is smaller, which means you can get the job done in less time, which means you has a faster system, right? Okay. For system, let's say with omega n equal to 2, normalized time omega nt means 2 times t, meaning that each unit normalized time corresponds, which means this is 1, okay, in this case, t equal to 0.5. Now, let's assume omega n, the value of omega n is no longer 2, but 0.5, all right? And in this case, if omega nt is equal to 2, then t become 2, all right? Now, remember that omega nt in this case, both cases are all 1. Tau is 1. The value of tau is 1 in both cases, okay? But with different natural frequency, their speed of response can be revealed by the value of the real time, which is t, all right? Okay, so this is the very reason why these slides tell us that omega n sets the over speed scale, okay? Which means when omega n is larger, the speed is faster. End of story, period. All larger omega n always represents fast response. Okay, always means fast response. Why is that the case? Remember that omega n is defined as this, right? How can a spring mass system, how do you make a spring mass temper system move faster? First thing, you have large K. Very, very strong spring constant. Very, very large, strong, very strong spring, and with a very, very large spring constant. So once you put the mass, it will produce a very large force to counteract the applied force. Okay, and as a result, the mass will move very, very fast. And how to make mass moves even faster? Easy. For the same amount of force, how do you generate larger acceleration? By reducing mass, right? So small mass, high spring constant is the formula for higher natural frequency. And higher natural frequency, when you go back to the roots, to the very nature of the spring constant and mass, you understand why natural frequency relate directly to speed of response of the system. All right? Okay, so simple physics. Direct the relationship is very, very straightforward. Okay, there's nothing fancy, nothing complex. All right, okay. This is another plot for the state response of a spring's mass temper system. Okay, this apparently is an underdamped case, and we have envelope here. Okay, and this envelope, of course, come from here. Okay. Now, let's check out some real examples. All right. Let's say we have a second order system, which if you solve the rule for this characteristic equation, you'll see that you have two roots, which correspond to two poles of this second order system. Okay. One is located at -1146, and the other is located here. And this will be the unit step response of this system. And this curve is actually what this unit step response look like. Okay? Nothing fancy, nothing unexpected. Two real rules, overdamped system, no acceleration. Okay, now let's look at another example. Here, I have two repeated root poles come from this transfer function. Both poles are located at -3. So the unit step response looks like this. The first pole generates this mode. The second pole, which is the same, which has the same location as the first pole, produces this mode. And when you put them together, this is the unit step response of the system. Again, no surprise, because this is an overdamped system, no acceleration. Everything come out as expected. Now, let's check it out. Check out the two complex conjugate poles. Okay, now the transfer function becomes this. All right, from this transfer function, it's easy to see this is omega n squared, right? So omega n apparently is 3. Okay, and 2 eta omega n is 2, right? So eta omega n is 1. And since omega n is 3, so eta is 1/3, right? Okay, and minus eta omega n is 1 I'm sorry, minus omega n is minus 1 over 3 times 3. I'm sorry, times 3, which is 1. This is the reason why we have e to minus t here, because the envelope should be this, right? Now, and where does eta A come from? Easy. This is damn natural frequency, omega d, which is omega n times e minus eta squared, square root, all right? Anyway, the location of these two poles are plotted in this figure. And this is the mathematical expression of the units of its unit step response. And this is what it looked like when you plot it out, okay? No big deal. Everything come out as expected under them oscillations, okay? Now let's go one step further. Let's see, two imaginary poles, okay? Because this is our transfer function. So the poles are located at 3J3, 3J or J3 and minus J3, okay? And this is its unit step response. Because the poles are located on the imaginary axis, the system therefore is marginally stable, which means its response will not diverge. It will also not converge. It will just keep going, okay? The amplitude remain the same even when time goes to infinity, all right? Now, let's move to another important issue, measures from unit step response. Why do we want to study unit step response? Remember, we are engineers. When we study things, whenever we study things, we study them because it has some practical values, okay? Now, the reason why we want to study step response is by examining the resulting step response, we can come out with many measures which can help us to characterize the performance of the second order system. How fast the system is, how stable the system is, okay? We must have some measures to quantify them, okay? We cannot just use adjective. Oh, it is very stable. It is not so stable. Well, it is very, very stable, but not extremely stable. Okay, that all makes sense, but what does it really mean when it comes to engineering applications? When it comes to engineering applications, we need numbers, okay? What is the horsepower of this engine? You cannot tell me, oh, very large horsepower. The horsepower is very large. I understand it is very large, but how large? Oh, it is very large. It is extremely large. It's larger than previous engines. That's all very good. Give me a number so I can actually comprehend the power of that engine, okay? So there is an urgent need for measures that can help us characterize the performance of second order system. And the reason why we study unit step response is from the unit step response, we can define or we can specify measures that can actually help us characterize how good a control system is. All right. Again, this plot reviews the location of the poles. All right. Now, this figure represents a particular case of unit step response. From this plot, we can see several important measures. The first is from the unit step response of a second order system, we can define rise time, which is the time required for the waveform to go from, say, 0.1 of the final value to 0.9 of the final value, okay? So the rise time, this should be it. There are actually different definitions of rise times. In this particular case, in this definition, okay, this rise time corresponds to TR1 here of this figure. And it is the time required to go from 0.0 all the way up to 0.9, right? This is one definition of rise time. Another definition of rise time is go from 0, the time required to go from 0 to 1, right? Rise time, okay? It depends, okay? Different people use different definitions, but the basic concept remain the same, okay? Now, what is the peak time? The time required to reach the first or maximum peak, okay? This is the peak, okay? The time required to reach the peak is what we call peak time. And here, this is a correspond to the peak time, we have the largest response. And here, we define the overshoot, all right? Or percent of overshoot. The amount that the waveform overshoots the steady state or the final value at the peak time, expressed as percentage of the steady state value, okay? That's a typical fashion. In extracting overshoot, we use percent overshoot. Okay, finally, settling time. The time required for the transient damp oscillation to reach and stay within minus positive 2% of the steady state values, all right? In this case, all right? Because eventually, the system will reach steady states, but theoretically, that will take forever, all right? For, let's say, distance to go away completely. It will only become 0 when t become infinity, okay? But that is a mathematical idealization, okay? For practical purpose, I don't care if it really goes to 0. What I want is it is small enough, okay? Because in engineering application, there is always tolerance. We always have room of tolerance, okay? So let's say the room of tolerance here is minus positive 2%, okay? And you can examine the response. Once the settling time, of course, is defined as the time required for the transient damp oscillation to reach and stay within. First of all, it has to be inside this band, okay? This band of tolerance, okay? It has to go inside this band of tolerance, and it has to stay there afterwards, okay? Once you identify the time points which satisfy the about 2 requirements, you have the settling time, okay? So these are 4 important measures for us to use to characterize the performances of a linear time invariant second order system, okay? Now, the next thing we want to do is to relate them to damping ratio and natural frequency. Why do we want to do that? Because the first thing is that we know omega n and eta are 2 key parameters of the second order systems. And the second reason why is once I know the relationship between those measures and natural frequency and damping ratio, if, let's say, the measure itself is not satisfactory, and I need to adjust it, okay, I need to make them better. Let's say the peak time is not just small enough, and I need to recalibrate my system, okay, then I will have a very good idea. How do I do that? Should I increase the natural frequency or should I decrease the damping ratio? Okay, I need to know the relationship between TP and damping ratio and natural frequency in order for me to do that. Okay, so let's first determine TP, which is the peak time. Now remember that this is the unit step response for underdamped second-order systems. To determine the peak time, what we need to do is let's first take the derivative, because by definition, at the peak, the slope is zero. So we set this to be zero. And then we determine the value of t such so that this y dot can be zero, all right? And by doing that, we can determine that the corresponding time, which is, of course, the peak time, is this, all right? So TP is inversely proportional to omega n, which means omega n is larger, TP is smaller, right? When what does that mean? When I say TP is smaller, it means it will take less time to reach the peak. And then it means the system is faster because reaching the peak time requires less time, all right? So that is apparently a solid evidence to support that, to support the statement that a system has a faster response, okay? All right, and by substituting this TP into this expression, you can determine MPT, right? And this is actually the amount of overshoot. Times it by 100, we will get percent overshoot, okay? Now, one very important thing is that the percentage of overshoot is only related to damping ratio, all right? It has nothing to do with natural frequency. So if you encounter a system which turned out to be satisfactory, but with one important weakness, that is excessive overshoot. The overshoot is simply too large, okay? Then what you need to do is to tune eta, to tune the damping ratio. Don't do anything to the natural frequency because it won't help, because overshoot has nothing to do with damping ratio. Well, I'm sorry, natural frequency, okay? It is controlled directly by damping ratio, okay? Now, with this expression, this tells us once you have eta, you can determine the percentage overshoot, and we can go the other way around. That is, with this expression, okay, it means if you know the desired amount of overshoot, you can come back with eta, okay? Now, with such an expression, of course, you can plot this curve, which will tell you that whatever the eta is, you can determine the corresponding percentage of the corresponding value of the percentage overshoot, percent overshoot, all right? So as you can see, the percent overshoot decreases monotonically with the increase of damping ratio. End of story, okay, all right? So this curve is important because it tells you how to tune the damping ratio to obtain satisfactory overshoot. Okay, the second thing, okay? The next thing we want to do, we have identified peak time, right? The next thing we want to do is we want to determine settling time, okay? Now, remember that, again, this is the unit state response for the underdamped case, all right? All right, it's 11 o'clock. Let's, again, take a 10 minutes break. 好，OK，谢谢，谢谢。